Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. Welcome to the course of Theory of Automata CS311. It's lecture number 23, and today we will discuss about syntax analysis in compiler construction and design. Here is the outline for today's lecture. Today we will discuss about syntax analysis introduction, and we will see syntax analysis in some detailed view. So let's discuss syntax analysis. Syntax analysis or parsing is the second phase of a compiler. We called syntax analysis as a parsing in compiler construction. It has two names. First is called syntax analysis and the other one is called parsing. So both the names are similar or used interchangeably. A lexical analyzer can identify tokens with the help of regular expressions and pattern rules. So a regular expression is a pattern that matches a set of strings. We have studied regular expressions, and you know that regular expressions is a pattern that matches a set of strings. And lexical analyzer uses or identify tokens with the help of regular expressions. But a lexical analyzer cannot check the syntax of a given sentence. So this is the limitation of lexical analyzer, that it cannot check the syntax of a given sentence due to the limitations of the regular expressions. So there are some regular expression limitations. The first limitation is that they are very short. A lot of very complex information is compacted or stored into a few characters, like in the case of when you are developing your web applications and you are using to verify your email address in a web form. Then in that case, what will you do? You will absolutely will write a regular expression against a email field, and when the user enters an email in that field, the interpreter will check the syntax of the email with the help of the regular expression. And the second limitation of the regular expression is that they are can be difficult to design and debug, and they are only useful in extracting regular information, that is information that is provided in a limited number of known formats, and in many real life problems are not regular languages. For instance, let's suppose using a regular expression to try to parse HTML is really a bad idea. HTML contains far too many optional parts and special rules. So in that case, these are the limitations of regular expressions, and for these reasons, lexical analyzer cannot check the syntax of a given sentence. Regular expressions cannot check balancing tokens such as parentheses, because when we write a code, we enclose our block of codes in some special brackets like braces or parentheses, so that in this case regular expressions cannot check balancing tokens such as parentheses. This means that this is an opening braces, it must have a closing braces as well. So with the help of regular expressions, we cannot check balancing tokens, and for that reason we need some advanced form to check this syntax as well. This phase, which is called syntax analysis or parsing, uses context-free grammars, and which is recognized by push-down automata. We recognized context-free grammars with the help of push-down automata, and this phase, which is called parsing or syntax analysis, uses context-free grammars. As you can see, context-free grammars is a superset of regular grammars, as depicted in the following illustration. As you can see that context-free grammar is a superset and regular grammar is a subset of this context-free grammar. Regular grammar is either right or left, whereas context-free grammar is basically any combination of terminals and non-terminals. And we have seen in the previous lectures what is a terminal and what is a non-terminal, and in that case we have also seen some production rules in like in the case of context-free grammars. We have made this production rule: A implies alpha, and we replace A with alpha whenever we found A in the substring. Hence you can see that the regular grammar is a subset of context-free grammar, and regular expressions is the basis of lexical analysis, and it represents regular languages. On the other hand, context-free grammars is the basis of parsing, and it represents language constructs. So in that case, context-free grammar is a superset of regular grammars. It implies that every regular grammar is also a context-free. So try to remember this, or try to keep a note on this, that the regular grammar is also a context-free grammar, but there exist some problems which are beyond the scope of regular grammar. A CFG or a context-free grammar is a helpful tool in describing the syntax of programming languages. So whenever you want to describe or check the syntax of a programming language, so in that case we will use a context-free grammar, because a context-free grammar is a helpful tool to describe the syntax of a programming language. The same, that it is a superset of regular grammars. CFG is a superset of a regular grammar. So how syntax analyzers works? This is the same diagram which we have seen before. In this diagram you can see that the lexical analyzer is using regular expressions and finite automata to validate the input tokens. So this phase, which is called a regular expression or finite automata, is used to validate, let me write this as well, is validate the input tokens. Okay, we are using finite automata and regular expressions to validate the input tokens, or lexemes. We call lexemes when we are using lexical analyzer, and we are using the word of token when we are dealing with syntax analyzer. And here you can see that we are using a context-free grammar to check the syntax of a programming language. Okay, when you want to check the syntax of a programming language, we can use, or we will use a context-free grammar. So the output of lexical analyzer is the token, and the input to the syntax analyzer is also a token. So the output of one phase is an input to another phase, and so on. A syntax analyzer or a parser, they have the same name. Sometimes we call it a syntax analyzer, or sometimes we call it a parser. It takes the input of lexical analyzer, which is called tokens, and the form of token streams. Okay, there are the tokens will come in the form of a stream, a regular stream, continuous stream. So the syntax analyzer or a parser takes the input from lexical analyzer in the form of token streams, and after that the parser analyzes the source code, which are token streams in this case, against the production rules to detect any errors in the code. So the parser always keeps a dictionary of production rules which are very necessary to detect any errors in the code, because without the production rules the parser cannot analyze the source code. So with the help of production rules, the parser analyzes the source code and detect any errors in the code. Here the term error means syntax errors. The output of this phase is a parse tree. So this is the main point. In the previous case which we have seen, in the case of lexical analyzer, the output is token, and syntax analyzer uses those tokens, and as a result it will generate a parse tree. So the product of syntax analyzer is a parse tree. In this way, the parser or the syntax analyzer accomplishes two tasks. First, it parsing the code and looking for the errors. This process is in syntax analyzer, and after that it will generate a parse tree as the output of the phase. So this is what we called the byproduct or a product of the syntax analyzer. This is the byproduct or the product of the syntax analyzer. The output, we can also call it as an output. Okay, the output of the syntax analyzer is a parse tree. Parsers are expected to parse the whole code even if some errors exist in the program. So these are somewhat similar to the compilers in a sense that they are expected to parse the whole code, not line by line, but the whole code, even if some errors exist in the program. And parsers use error recovering strategies, which we have seen in many IDEs, in which the parser or the syntax analyzer will give you some highlights about the error. Why it gives those error highlights? Because the purpose is to recover those errors or correction. We call it correction. Okay, correction, recovering. Here the recovering means the correction. With the help of those errors, we can correct, or we will correct the programming errors. There is another concept in syntax analysis which is called derivation, and this concept of derivation is so much relevant to the parse trees. So let's see what this concept is. So what is a derivation? A derivation is basically a sequence of production rules. So the first point is derivation is a sequence of production rules in order to get the input string. So with the help of those production rules, we can get the input string. And during parsing, we take two decisions for some sentential form of the input. The first decision says that deciding the non-terminal which is to be replaced. This is a terminology in context-free grammars. Non-terminals are those which can be replaced by some strings in substrings, and deciding the production rule by which the non-terminal will be replaced. So when we are designing context-free grammars, we have different production rules for a particular non-terminals, and those non-terminals during compilation will be replaced by their respective values. So during parsing, we take two decisions. The first decision is deciding the non-terminal which is to be replaced, and after that we will decide which production rule we will use to replace that non-terminal. To decide which non-terminal is to be replaced with production rules, we can have two options. So in order to accomplish this condition, which says that which non-terminal to be replaced with production rule, we further have two options. The first option is called the leftmost derivation, and the second option is called the rightmost derivation. So let's see and dig in and see what these leftmost derivation option is and the rightmost derivation is. First, leftmost derivation. If the sentential form of an input is scanned and replaced from left to right, it is called leftmost derivation. So we always derive the sentential form of an input in some manner, that is from right to left or left to right. So when we scan the sequential form of an input and replace it with from left to right fashion, it is called leftmost derivation, and the sentential form derived by the leftmost derivation is called the left sentential form. Okay, so these two names can be used interchangeably. We called it as leftmost derivation, and the byproduct or the product of this leftmost derivation is left sentential form. So they have two names, leftmost derivation and left sentential form. Now describe this process, leftmost derivation, with the help of an example. Here you can see different production rules such that E is a non-terminal, and non-terminal is always on the left hand side, and it implies that E is also non-terminal, and it can appear on the right hand side as well. So on the right hand side we have seen, we can see these two non-terminals as well. Or this is the rule number one. We can see this, this is a rule number one. Let me annotate it so that we can use these rules in the derivation. And this is rule number two. Here you can see this is a steric, only this is for plus sign and this is for multiplication. We have two rules. One is for addition, the second one is for multiplication, and the third rule is for simple assignment to a terminal. Okay, this is called a terminal. And let's say we are going to check this input string id plus id into id. So how this how these rules works when we derive in leftmost derivation. So let's go on and see. Okay, in this part here you can see that we have used this rule, rule number two. We have used this rule number two on the top, and then we have a plan to replace it in a leftmost derivation way. As you can see from the statements that we have replaced this E with this E, because E is equal to E plus E. So we have derived in a leftmost fashion and change this part of the expression. Similarly, as you can see, we again derive and replace this part of the E with id, because this is rule number 3. This is rule number 3. We have replaced E with id, and after that we have replaced this second E with an id. We have again used rule 3, and so on. Here you can see we have replaced these two E's with their corresponding IDs, and at the last we have only one E, and at the last we have only one E, so that in the next step we have replaced this I with ID as well. So this is called the leftmost derivation. Now see the rightmost derivation. If we scan and replace the input with production rules from right to left, then it is known as rightmost derivation. Similarly, we can also call this rightmost derivation as right sequential form. The sentential form derived from the rightmost derivation is called the right sentential form. So it has also two names. One is called the rightmost derivation and the other name is right sentential form. Both names can be used interchangeably. So let's see this rule with the help of an example. Rightmost derivation, they, as you can judge from the statements, they are the same production rules, and this is the same input string, but the order we want these rules in the rightmost derivation. So let's take this first rule and replace, as you can see that we have replaced this part in the rightmost derivation. We have replaced this E with this E steric E, because E is equal to E steric E, and after that we have replaced this E, the last E, with this value which is over here, and similarly we have replaced this E with ID and this E with ID. So this is the last sentence which is a result of this phenomena which is called rightmost derivation. Now let's see a parse tree. What is a parse tree? Because we have seen the leftmost derivation and the rightmost derivation. These two concepts are used in a parse tree. So what is a parse tree? A parse tree is a graphical depiction of derivation. As I said, the derivation is a concept which we can see with the help of a parse tree. So if you want to see a derivation, you can depict or illustrate that derivation with the help of a parse tree. Okay. So this is the graphical representation of a derivation. Parse tree is a graphical representation of a derivation, and it is convenient to see how strings are derived from the start symbol. So this is the main purpose of this parse tree, that with the help of parse tree we can see that how strings are derived from the start symbol. And the start symbol of the derivation becomes the root of the parse tree. This is the main point, that the start symbol of the derivation. Here the start symbol means from where we started our derivation, either leftmost or rightmost. In that case, the start symbol will always appear as a root node of the parse tree. For example, we take the leftmost derivation of this expression a plus b into c. The leftmost derivation is this. As you can see, we replace this e with this e, the same production rule we have seen, and at the last we have also see this last statement. Okay, so this is the same production rule which we have seen in leftmost derivation and rightmost derivation. And in step 1 we can see the root node. Here the root node is e, because we have started from this e, so that reason this is the root node of this tree. Here you can see that we have used this e and then static operator in between, and the two nodes, the left node and the right node. The same example, and now because we have replaced this e with this, the first e is replaced by this and the second e is replaced by this, the leftmost derivation with id. This is the first e, and you can see that we have replaced this e with e plus e. This is the part we have replaced. Okay, this is the root node, and these two nodes are treated as the child node. This is the second statement. Will come over here, and this is the first part of the tree. This part. Same derivation rule. Here you can see that we have replaced this id e, this e with this id. So this is the first part of the, this is the first part of the tree, and this is the second part of the tree. Okay, here you can see that this is the second part of the tree, and this id is will appear over here. So with the help of these derivation rules, we are creating a parse tree. Similarly, you can also judge that we have included this these two IDs as well over here as a result of this phenomena, to incorporate this phenomena. Okay, this is that part. The same rule, and now you can see that we have used this statement, the last expression, with this tree. So with the help of parse trees, we can visualize the derivation process, either the leftmost derivation or the rightmost derivation. We can visualize. The parse tree is a visualization. We can say that the parse tree is a visualization technique. Is a visualization technique to see the derivations in action. This is for the visualization. In a parse tree, all leaf nodes are terminals. This is the main point, and all interior nodes are non-terminal, and an order traverser gives original input string. You have studied in your previous semesters the traverser methods of different trees. In order traverser is that order in which the operator comes in between, so that's why we call it in order traverser. You have studied this concept, which is called in order traverser, pre-order or post-order traversing methods of a tree. So try to remember these points. All leaf nodes are terminals, and all interior nodes are non-terminals, and in order traversal gives the original input string. A parse tree depicts associativity and precedence of operators, either leftmost or rightmost. The deepest subtree is traversed first. This is the main rule, that the deepest subtree is traversed first. Therefore, the operator in that subtree gets precedence over the operator which is in the parent node. So this is the default precedence rule, in a sense that the deepest subtree is traversed first. Therefore, the operator that comes in that subtree will get the precedence with having high priority, which is in the parent node. There is also a concept in grammars, and that concept is very crucial to the parse tree, and that concept is called ambiguity in the grammars. So what is an ambiguity in the grammar? A grammar G is said to be unambiguous if it has more than one parse tree. So again, you can see that the ambiguity comes because of this concept of parse tree. A grammar is said to be unambiguous if it has more than one parse tree. That parse tree either would be left or rightmost derivation for at least one string. So there are multiple strings, but the condition is for at least one string. Example, we have seen these production rules. These are called production rules, and for the string id plus id minus id, the above grammar generates two parse trees. For one sentence, we have two parse trees in a grammar, and for that reason we can say that the grammar is unambiguous because it has this parse tree and it has this parse tree. So the same sentence, for the same string, we have two parse trees, okay, two trees. That's why the grammar is said to be an ambiguous one. The language generated by an ambiguous grammar is said to be inherently ambiguous. So this is the effect of ambiguous grammar. Any language generated by the ambiguous grammar is also ambiguous. Ambiguity in grammar is not good for compiler construction. We have to remove it or eliminate it completely. And no method can detect and remove ambiguity automatically, but it can be removed by either rewriting the whole grammar without ambiguity or by setting and following associativity and precedence rules, constraints. So this is the most recommended method, which is called associativity and precedence rules. We can eliminate or remove or control the ambiguous grammar error with the help of using these rules called associativity and precedence constraints. The first method is also very useful, but instead of rewriting the whole grammar without ambiguity, the second option is more favorable than the first one. What is associativity? If an operand has operators on both sides, let's say we have two operands a plus b and the operator is in between, which is the plus. Any arithmetic operation, the side on which the operator takes this operand is decided by the associativity of those operators. Okay, so this is the technique. If the operation is left associative, then the operand will be taken by the left operator, or if the operation is right associative, the right operator will take the operand. So these are the by default rules which says that if the operation here the operation means this arithmetic operation is left associative, then the operand here a or b will be taken by the left operator, or if the operation is right associative, the right operator will take the operand. The decision is based on this operation. Let's discuss this with an example. Operations addition, multiplication, subtraction and division are left associative, so these operations will take the left operand. If the expression contains id, op, id, this is the generic syntax, operands and operations, it will be evaluated as id, op, id, op, id. We have shown associativity with the help of this parenthesis. For example, id, plus id and plus id. So the first, because it is left associative, that's why we take this left part. This is the right part and this is the left part. So because this is a left associative, so that's why we have included this parenthesis. Operations like exponentiation are right associative, that is the order of evaluation is the same, expression will be the generic syntax. As you can see, if two different operators share a common operand, the precedence of operators decides which will take the operand. That is 2 plus 3, and after that 3 * 4 can have two different parse trees, one corresponding to 2 plus 3 and the other corresponding to this one. By setting precedence among operators, this problem can easily be removed. As in the previous example, mathematically, as we can see, this has precedence over this operator. So the expression 2 plus 3 into 4 will always be interpreted as in this way. These methods decrease the chances of ambiguity in a language or its grammar. So with the help of these methods, we can reduce the ambiguity by using the concepts of precedence and associativity in our grammar. There are some limitations in syntax analyzer. Syntax analyzer receives their inputs in the form of tokens from lexical analyzer, and lexical analyzers are responsible for the validity of token supplied by the syntax analyzer. Syntax analyzers have the following drawbacks. It cannot determine if a token is valid. So this step is done in lexical analysis phase, and it cannot determine if a token is declared before it is being used. So this is the limitation. And it cannot determine if a token is initialized before it is being used. Here there are two different things. This is initialize and this is declaration. Declaration is different from initialization. And it cannot determine if an operation performed on a token type is valid or not. So these are the limitations of syntax analyzers. So how can we remove these limitations or drawbacks of the syntax analyzer? The answer is with the help of semantic analyzer. With the help of semantic analyzer, we can eliminate or remove or check these drawbacks or disadvantages. So the compiler has initial three phases. The first phase is called the lexical phase, where we use finite automata and regular expressions. This is the first phase of a compiler design or construction. After that, we have seen in today's lecture syntax analyzer. The purpose is to check the syntax. This is the second phase of a compiler, and the third phase is semantic analyzer. Here we have used automata, finite automata and regular expressions, and in the second phase of a compiler we have used CFGs. Okay, we have used context-free grammars. So after that you have basic knowledge of why we have studied finite automata and context-free grammars and context-sensitive grammars and non-deterministic finite automata. These terms or these phases or these concepts are using different phases of a compiler. So this is the third phase, which we'll study later on. I hope you have understood today's lecture. If you have any questions regarding today's lecture, you can email me. I will reply you, and hope for the best. See you in your next lecture, inshallah.